This is Dr. Smith. I wanted to go ahead and work through the in-class problems that we did just the other day in class. This is in-class problems from multiple linear regression talking about dummy and quadratic variables. This is a fairly straightforward in-class problem. It uses a lot of the things we talked about in class, and so this should be fairly short, but that's my famous last words. So we always start off these kind of problems. I always try to give you a bit of the scenario, so it always helps to read through them. So in this case, I'm just going to read this top paragraph here. We have data on 1,260 people's hourly wage, their years of experience, education, their beauty, which is in the looks variable, which is rated 1 to 10, with 10 being the highest, and several dummy variables for if they're in a union, are in good health, are black, are female, are married, live in the South, live in a big city or small city. The excluded variable there would be medium city, and if they work in a service industry. And so now we're going to answer some questions about this. Here you have the full regression output. Notice there's nothing to fill in here. This is exactly how it would have come out of Excel. Notice we do have our number of observations here, which is 1,260, which is exactly what we said we did, so that everything's matching up pretty well. Just to point out, we have an R squared of about 24%. So we're explaining, a quarter of the variation in people's wages using these variables here. So we have a lot of different variables. This is one of the bigger models that we've come across. We have people's experience. We have their, we have their education. We have that looks variable. We have if they're in a union, in good health, black, female, married, South. If they live in a big city, if they live in a small city, and if they work in a service occupation. So now let's just go down here. Let's jump into the question. So number one, how does someone's beauty score affect their hourly wage? Let's stop there. Let's just answer that question. So someone's beauty score is captured in the looks variable, right? So the looks right here. And anytime you're wanting to see how one variable affects another, what we want to do there is we want to look at the coefficient on that variable. Because remember, the coefficient is essentially the slope, and the slope between an x and a y tells us about the relationship. So we want to know, what is that relationship? And so that coefficient is 0.440657, yada yada. We'll just say 0.44 for now. So what that means is that if someone's beauty score increased by 1 point, so going from, say, a 6 to a 7, or from a 9 to a 10, then we would expect, on average, that increase in beauty to be associated with a 44-cent increase in their hourly wage. So a lot of questions I got the other day in class were, how do we know if this is 44 cents, or is this $44, or $440? How do we know? Well, it all depends on what the unit for our dependent variable is. Now here our dependent variable is hourly wage. And think about, how do we usually talk about hourly wage? Well, hourly wage is measured in dollars, right? You make 40, it'd be nice if you made 40-something dollars an hour. Right, you might make $7.50 an hour, or you might make $12 an hour. So usually when we talk about hourly wage, we talk about it in dollars per hour, and so that's how this is measured. And so what this here, the 0.44 means, that is $0.44 per hour, which is 44 cents an hour. And so an increase of your looks by 1 point, we would expect to see on average an increase in your pay of about 44 cents an hour. So that's how you answer that first part of that question. It'll come down, so is that result significant at the 5% level? So anytime we're talking about if something is significant or insignificant, when given some level of significance, in this case 5%, what you always want to go do is you want to go look at the p-value for that variable. So for the looks variable, its p-value is 0.01086, yada, yada, yada. So a little bit bigger than 1%. Remember, we can talk about p-values in percentage terms. And so the p-value here is slightly bigger than 1%. And so we come down here and say, so is the result significant at the 5% level? Well, so the way that we tell if something is significant or not, we would say that if our p-value is less than our level of significance, so in this case, is 1% or slightly bigger than 1%, smaller than 5%? And it is, right? 1 point something percent is definitely smaller than 5%. And if that's the case, then we say this relationship is significant. There's a lot of ways to say that. Sometimes we say the relationship is significant. Sometimes we just say the variable is significant. However we say it, we tend to say, that's the same thing as saying we reject the null. So if you remember, in our last test, we kept talking about the null hypothesis and the alternative hypothesis. The null hypothesis is that there's no relationship, right? That beta equals 0. So in this case, we're rejecting the null because our p-value is less than 5%. And by rejecting that null, we're saying a relationship does exist. We have enough evidence to say a relationship exists. We call this a significant variable or a significant relationship. Now, what about at the 1% level? Well, again, we're going to compare our p-value, which is slightly bigger than 1%, to our significance level, which is 1%. So in this case, a lot of people are like, well, it's 1%. Well, it's a little bigger than 1%, and so, you kind of think of the way, is $1.08 the same thing as $1? No, it's a little bigger than $1. So in this case, this is 1.08%. And so that's a little bigger than 1%. And so since our p-value is bigger than 1%, then this is not significant, right? We would fail to reject the null. That means we don't have enough evidence to say at the 1% level. So to be 99% sure, we don't have enough evidence to be 99% sure. We almost do, but we don't. And so since we're not 99% sure, then we would fail to reject the null or say it's insignificant at the 1% level. Okay, so let me just type that in down here so we know how to do everything that we're doing. So to answer that question, how does someone's beauty score affect their hourly wage? Well, we would expect a 1 point increase in beauty to cause, on average, a 44-cent increase in hourly pay. This relationship is significant at the 5% level, but not at the 1% level. Okay, fantastic. Let's move down to question 2. What is the predicted hourly wage for someone who has 10 years of experience, 14 years of education, a beauty score of 6, is not in a union, is in good health, is a white woman who is married in a small city in the South who works in the service industry? It's a lot of information. Essentially here we are going to be using our y-hat formula. We want to predict hourly wage. And essentially we're just going to be plugging in values for each of these variables, for every single one. You can't leave any of them out. We're going to plug in a value for every single one of those variables and multiply those values times their coefficient. So let's do that. It's going to take me a minute to type it all out here, but let's see what happens. So I'm going to do this in the equation editor. You would obviously just write this out, but this is easier for me to do here. So the first thing, a lot of people forgot this the other day, so we're going to have y hat, and I can actually do this a little fancier because I'm in the equation editor. We're gonna do y hat here. Ta-da, y hat. Okay, y hat is equal. So this is our predicted y. Is going to be the first thing you want to have is your intercept. So I'm going to take this out to 4 decimal points here. You can do 3 or 4. I'm going to use 4 just to make sure I'm super accurate. So we always want to start with your intercept, and then from there on, we're going to be multiplying basically each value times its coefficient, right? So the first variables that we have show up in our regression output up here, Now, I would say at this point, I'm actually looking at a printout right now, so I don't have to keep scrolling up and scrolling down. I would suggest while you're watching this video, have this either printed out or open next to you so you can, you're not scrolling all over the place. So I'm not going to be scrolling up and down. So if you're wondering, where's he getting these numbers? I'm getting them from the chart that's slightly off the screen, but you should have printed out in front of you. Here we go. So the next thing we have is experience. So this person has 10 years of experience. So we're going to do our coefficient, which is 0.2423 times the value of experience, which in this case, she has 10 years of experience. Okay. The next we have experience squared. So that is a negative 0.00384. Oh, I forgot my negative there. Times experience squared. So that's going to be 10 squared. Okay, so that threw a lot of people the other day. They're like, oh, well, we don't need to use the square one. Yeah, you have to use every single variable that we have. So just to recap, here's our intercept, okay, plus this is the coefficient on experience times the level of experience, plus the coefficient on experience squared times the value for experience squared, so 10 squared. Okay, so we're just going to keep plugging through this. The next thing we have is education, which is a negative 0.1822 times the value of education. She has 14 years of education. Okay, plus 0.0240. That's the value in education squared times her education squared, so 14 squared. Okay, plus her looks, 0.4407 times her look score, which is 6. Okay. Now everything after this is a dummy variable. You still do it the exact same way, except for remember the values for a dummy variable are going to be a 1 or a 0. It's a 1 if you're in the group. It's a 0 if the person's not in the group. So otherwise, we do this exactly the same as all the other variables. So union. Our data up here says she's not in a union, but we're still going to put the coefficient there. So 0.5380 times she's not in a union, so the value is a 0. Next, she is in good health. So you put the good health coefficient, which is negative 0.0374 times she is in good health, so that'll be a 1. Okay. Plus, she's white. She's not black, and the variable here is black. So the coefficient, we'll still put it, negative 0.0526 times she's white, not black, so she gets a 0. Okay. She is a woman, so she is female, so 2.0807 times 1, because she's a woman. Okay. She's also married, so 0.6586 times 1. Okay. Plus, she lives in the South, so 0.3758 times 1. Plus, she doesn't live in a big city, so this will be 1.8138 times 0. Plus 0.6621. This is for a small city, which she does live in, so that'll be a 1. And then finally, she works in a service industry, so the last part is negative 0.6797 times 1. So that is the full equation there. Now, I will say, on the exam, I'm not going to make it that long. Okay, I knew you had some time in class to really work through this, and I wanted to kind of drive the point home, how you do it. On the test, I won't make it that long, but you can still see how you would plug in for every single one of those variables. So now I'm just going to take this real quick. I'm going to copy it I'm going to just take it out to Google. Let's see. Hey, there's my email. Let's see. Let's go to Google real quick. Let's use Google as a calculator for us. We'll hit enter. Oh, come on, Google. We'll use Wolfram Alpha, which if you've never dealt with Wolfram Alpha before, it's basically like a super powerful calculator. And it does all kind of things. But we'll plug that in there. And this will actually evaluate it as a math equation. Hopefully. There we go. And let's see. And so we see our result is 5.9469. And so I'll go type that in over here, wherever we're at, which is equal to 5.9469. There we go. So basically, we would expect this person's pay to be, we would predict it to be about $5.95 an hour. Okay? Ooh, that was fun. Okay. So let's come and look at the next question. What is the impact of being married on hourly wage? So being married, we're going to come up and look at our married variable. Again, anytime we're talking about the impact or the effect of one variable on our dependent variable, we're going to go look at our coefficient because that is the impact. That's the slope. So we come here and we see the slope for married is 0.6586. So what that means is then the impact of being married on hourly wage. So we would expect everything else the same, that someone married would make 0.65 something, 6586. So basically almost 66 cents more per hour than someone who's not married. And again, we're qualifying that, saying everything else the same. So having the same education, same experience, they live in the same area, all that being the same. You know, one person's married, one person's not. We would expect someone who's married to make about 66 cents more per hour than someone who's not married. What about being black? Well, we're going to basically retype that exact sentence. We would expect everything else the same, that someone who is black to make, and come look at our, here, black is negative 0.0526. So to make basically 5 cents less than someone who was not black. Okay? Are those results significant at the 5% level? So let's come up here and look. Well, the p-value on married is a little bit bigger than 1%. So that is significant at the 5% level. However, the p-value on black is like 90%. So definitely bigger than 5%. So we'll come down here and we'll say the relationship between married and hourly wage is significant at the 5% level, but the relationship between black and hourly wage is not significant at the 5% level. Okay? Here we go. So number 4, write out an equation to calculate the relationship between experience and hourly wage. Now, usually, right, if we weren't dealing with these quadratic terms, right, the relationship between an x and a y is just a coefficient, not hard at all. But in this case, if we come up here and look, we're talking about experience in a second. We'll talk about education as well. Notice we have an experience and an experience squared. So anytime you have a quadratic term, that experience squared, or education squared, or square footage squared, or bedroom squared, whatever variable you have, and you have the squared term, you have to use that slope formula that we talked about in class. And just to remind you what that slope formula is, I'm going to type it right here. that slope formula, slope was equal to beta, so I can do this, underscore linear plus 2 beta quad times x. Okay, so that was the equation that we dealt with, that we said we needed to plug in to find that relationship between some x variable that has both a linear and a quadratic term. And so in this case, we're going to use that equation here. Okay, so to do that, let's start by looking at experience. Well, let's come up and look and say, and again, for those of you who've had calculus, you recognize this as a derivative. Okay, this is basically the derivative of the population model with respect to, say, some x that has both a linear and a quadratic term. Okay, so for those who don't have calculus, ignore everything I just said. So we're going to come up here. We're talking about experience first. So the beta linear, the coefficient on the linear term, okay, in this case we estimate that to be 0.2423. So that's the linear term. That's the one that's not squared. So if it's not squared, it's the linear one. Okay, so we're going to come down here, and then so the slope, let me do this in an equation. Slope is going to be, our beta linear is 0.2423 plus 2, again, always a 2, times beta quad. What's our coefficient on that quadratic term? The one that is squared is the negative 0.00383. Okay, so negative 0.00, actually it's 384 with rounding. Okay, that's the coefficient, times, in this case, your x variable. In this case, we're talking about experience. So we'll just write it just like that. Okay, so that is the formula to give us the slope, the relationship between experience and hourly wage. We'd have to remember that relationship depends on the level of experience. That's why we added in that quadratic term. And so we have to be given some level of experience to actually calculate what that slope is. All right, so that's what questions 5 and 6 are going to do in just a second. But right now, we don't know what the experience is. We just have this. Now, we're going to do that same thing for education. So the slope for education, coming up here and looking at what our linear term is. Linear is the one that's not the squared term. Negative 0.1822. So we'll come back down here. Is going to be negative 0.1822 plus 2 times the quadratic term. I'm going to come up here and see what is our quadratic term. Quadratic term is 0.0240. So 0.0240 times your x. In this case, our x is education. Okay, so that's our two formulas that we deal with here. Next, what do we expect the change in hourly wage to be for someone who has 14 years of experience gaining 1 more year, so going up to 15? The way that you would usually answer that question, right? If someone was gaining 1 year of experience, you would go look at the coefficient. Well, we can't do that here because, again, we have this quadratic term for experience. So we have to use the formula that we have right up here, this slope formula for experience. Okay, that's the one that we're going to use here. So we're going to plug into that formula. So the slope, let's use this. Let's see, slope is going to be equal to 0.2423 plus 2 times negative 0.00384 times our level of experience. In this case, we have 14 levels of experience, 14 years of experience. So we just plug in there, okay? So we grab our handy-dandy calculator. I won't spend time going out to Google for this one. I can just type it in pretty darn quickly. 2423 plus, we'll do this in parentheses. Let's see, 2 times 0.00384, and we'll make that be a negative, times 14, close parentheses, And so we get 0.13478. So 0.13478. So what this means is we would expect going from an increase of 1, so going from 14 to 15, we would expect the change in the hourly wage to be about 13 cents, a little bit more than 13 cents, okay? So not hard there. Okay, for number 6, how would we expect the hourly wage to change when someone's gaining 1 year of education, going from 12 to 13? So now we're going to plug into our education formula here. Okay, so let's do that. So the slope is equal to, okay, let's scroll up just a little bit, negative 1822 plus 2 times 0.024 times, in this case, 12. Okay, and that's going to equal, let's use our calculator to do that. Okay, calculator, so we'll say 0.1822, we'll make that negative, plus, use some parentheses here, 2 times 0.024 times 12, close those parentheses, hit enter, so 0.3938. So from gaining 1 year of experience, going from 12 years to 13 years of education, we would expect an increase in pay of almost 40 cents an hour. So that's a pretty big jump. Okay. Finally, question 7. At what level of experience does experience not affect the hourly wage? What about education? Well, what does it mean to not affect hourly wage? Remember, the effect is the slope. So if you're not affecting hourly wage, that means the slope is equal to 0, right? There's no effect. And so if that's the case, then we have an equation for the slope up here in question 4. We have 2 equations for slope. What we're going to do is we're going to set each of them equal to 0. Okay, so we're going to come here and we're going to say slope is equal to 0. So 0, let's do this in an equation. 0 is going to be equal to 0.2423 plus 2 times negative 0.00384 times, in this case, our level of experience. Okay, what we're going to do is we're going to solve for our level of experience. Okay, so how do we do that? Well, the first thing that you're going to do, the first thing we'll do is we'll subtract both sides. Subtract from both sides, we'll subtract this 0.2423. Okay, and so what that does is that leaves us with, let me see if I can be awesome here. Just kidding. Let's see. I should probably edit this out later, but I'm not going to because I'm lazy. Ha! Oh, look at that, right arrow. Okay. What that leads us to then is negative 0.2423 is equal to 2 times 0.00384. Okay. Oh, forgot my negative. Times experience. Okay. So then what do? Well, we want to solve that, again, get experience by itself. So we're going to divide both sides by the 2 times the negative 0.00384. So get our right arrow again here. What that leads us to is then negative 0.2423 divided by 2 times negative 0.00384 is equal to experience. We're going to plug that into our calculator. So we'll come down here and grab a calculator. So we'll do, that one should be negative there, shouldn't it? Okay, because it's negative over here when we moved it. So grab our calculator. End up with, oops, let's see. 0.2423, make that be negative, divided by 2 times 0.00384, make that be negative, close that parentheses, hit enter, and we get 31.55. So experience is equal to 31.55. So once you hit 30, about 32 years of experience, somewhere between 31 and 32 years of experience, your experience stops mattering. There you go. Okay? That's what that tells us. So up until that point, experience is increasing your pay. But after 31, it's not increasing. In fact, this model would say it'd be decreasing your pay after 31. That's not exactly probably accurate, but at least at this point, according to this model, at 31, somewhere between 31 and 32 years, your experience stops mattering. Okay, that's where that's, the slope is equal to 0. Now we can do the exact same thing here for education. At what point does your education stop paying off? Well, we'll increase, means we'll put in our equation here. So we're going to get 0 is equal to, and here we're going to set this one equal to 0, so 18.1822 is equal to 2 times, somehow I jumped out of my equation there, is equal to, plus 2 times 0.024 times our level of education. Okay, so we want to solve for that level of education. Come on, computer. It worked so nice a minute ago, didn't it, guys? There we go. Okay. Now, so how do we solve for that? Well, we again, just like we did above, we need to move this negative 0.1822 to the other side. So we're going to add 0.1822 to both sides. We end up with 0.1822 is equal to 2 times 0.24 times education. Okay, everybody with me there? Is that a positive? Yeah, that's positive. Okay, so it's 0.24. Okay, and then we're going to then come here. We're going to solve for education by dividing by 2 times 2 times 0.024. So it doesn't like me today, guys. I don't know why. Okay, well. Just talk amongst yourselves while I fight with word here. Okay. Well, you figure out what I'm trying to do. Okay, we'll do it the hard way. Come on. We'll do it that way if we have to. Okay, then that leads to, we're going to divide both sides by, so we end up with 0.1822 divided by 2 times 0.024, which is equal to the level of education. So we literally just plug that in to our calculator. And we get 3.795. So we'll say 3.8. All right. So what that is telling us is basically, you might think, okay, well, so what we're saying is at 3.8 years of education, that's not changing your pay. Okay. What we saw a minute ago is that, at 12 years of education, it was a positive effect. And so what we can basically tell at this point is that basically everything after 4 years of education, that's going to be increasing your pay. Don't worry about how to really interpret that. But the main thing here is to see is that that there's no effect of pay at, say, 3.8 years of education. After that, it's actually a positive effect, and so it'll be raising your pay after that. Okay, but that's the whole thing, right? So, fantastic. Let's see. So, if you have any questions on any of that, feel free to email me or talk to me in class. Otherwise, we'll continue moving along, and we'll have a video for our next in-class problem in about a week or so. Otherwise, see you in class, guys.